Deep beneath our feet, trapped under absolutely crushing pressure, oil isn't just some simple black liquid. No, it's got a complex, kind of hidden personality. And figuring out that personality is the key to unlocking our energy resources. So today, let's play petroleum psychologist and figure out what really makes this stuff tick. It all boils down to this one huge billion-dollar question for petroleum engineers. You've got this incredible resource, thousands of feet down, right? But how in the world do you produce it in the most efficient way possible? How do you make sure you get the absolute most out of it? Well, the answer, and you might find this a little surprising, starts with something that looks a whole lot like a medical checkup. Think about it. Before you can treat a patient, you have to understand them, right? And in our case, the patient is the reservoir fluid itself. Okay, so let's jump right into our diagnosis. And believe me, the stakes here are incredibly high. Getting this right is the difference between an efficient, booming energy source and leaving tons of valuable resources stuck in the ground. So this is our patient, the reservoir fluid. And it's not just plain old crude oil. It's this super pressurized cocktail of all kinds of different hydrocarbons. We're talking everything from super light gases like methane to really heavy, complex molecules. And the secret to everything is understanding how this whole mixture behaves when that pressure starts to change. So, first things first, in any good checkup, right, you gotta get the basics. What is this patient actually made of? We need to decode the fluid's DNA, and to do that, we need an ingredient list. And here it is. This is what's called a compositional analysis. It's basically the fluid's unique chemical fingerprint. It tells us the exact percentage of every single component, from the lightest little gas molecules to the heaviest, gooeyest oils. You really want to think of this as the master key. This incredibly detailed breakdown is the foundation for predicting everything else that's going to happen. And hey, don't just take my word for it. As the Reservoir Engineering Handbook says, this analysis is, quote, the most complete description of reservoir fluid that can be made. With this DNA in hand, we can finally start to predict how the fluid is going to act. All right, next up in our checkup, the stress test. We have to see how our patient reacts under pressure, literally. So we take a sample of the fluid, we put it in this specialized lab instrument, and we perfectly recreate the extreme conditions found deep, deep in the earth. Now, engineers run two main types of these stress tests. The first one is called a constant composition test. The best way to think about this is like shaking a soda bottle, but keeping the cap sealed on tight. You lower the pressure, gas bubbles out like crazy, but it's all trapped inside. The second one, the differential liberation test, is more like slowly, carefully twisting that cap and letting the gas hiss out and escape. And this slide just illustrates the difference perfectly. Okay, first let's look at the left side. That's our sealed system, the constant composition test. As the pressure drops, you can see that gas bubbling out, but it stays right there in the cell with the oil. Now look over to the right at the differential liberation test. See how at each step, that gas that's bubbled out gets removed from the top? This is a huge deal because it completely changes the makeup of the oil that's left behind. So the whole point of that first sealed system test is to find one critical number, the bubble point. That is the magic pressure where the very first tiny bubble of gas appears. It's an absolutely crucial vital sign for the health of the entire reservoir. Now that second open system test is so important because, well, it's a lot closer to what actually happens down in the reservoir. As gas bubbles out of the oil, it's so much lighter and less viscous that it can just flow away, leaving the heavier oil behind. So this test simulates that separation process, but it only tells us about half the story of the fluid's entire journey. Because after that long journey from miles underground, our fluid has to go through one last process at the surface. Our checkup has to simulate this final step, from the well through all the surface equipment and finally into the stock tank. And up here on the surface, the whole game changes. It's all about optimization. In these big tanks called separators, engineers are hunting for that perfect Goldilocks pressure. Not too high, not too low, but just right to squeeze the most liquid oil into the final storage tank. See, if the separator pressure is too high, the process just isn't very efficient. You get what's called a higher oil formation volume factor, which is just a fancy way of saying the oil shrinks a lot on its way to the surface. And a higher number is bad. It means more shrinkage. In this case, it takes almost 1.5 barrels of fluid from the reservoir just to make one single barrel of sellable oil.
But by lowering the pressure to that just right Goldilocks level, we get a much better result. We knock out the perfect amount of gas, and we maximize the final liquid. Now it only takes 1.474 barrels. I know, that doesn't sound like a big difference, but when you're producing for decades, that tiny little optimization adds up to millions of extra barrels of oil. It's a huge deal.
So the bottom line is, this final lab test makes sure that the fluid's journey to the surface is as efficient as humanly possible, maximizing every last drop of the final product. Okay, the checkup is complete. We've run all of our tests, we've got data on the fluid's DNA, its behavior in the reservoir, and its trip to the surface. Now comes the most important part of all, the final diagnosis. But here's where it gets really tricky. The reservoir simulation, that differential liberation test, it gives us one set of results. And the surface separator test, it gives us another. The problem? They don't match. So which one do you bet your multi-billion-dollar production plan on? And the brilliant answer is neither. Or maybe a better way to put it is both. An experienced engineer knows you can't just pick one. You have to cleverly combine the data from both of these tests to create one single accurate forecast for the future. This graph right here shows the problem perfectly. See that smooth blue curve sloping downwards? That's our prediction for how the oil behaves deep in the reservoir as the pressure drops. But you see that single dot way off the curve? That's our actual real-world measurement from the surface equipment. They just don't line up, and that gap represents a multi-million-dollar problem. And this is the elegant solution. Engineers don't throw either piece of data away. Instead, they use these established formulas to basically anchor the shape of that reservoir curve to the real-world endpoint from the surface test. This creates what's called the adjusted bow curve, a single, reliable forecast that honors both realities and accurately models the fluid's entire journey from start to finish. And that is the whole point of this entire painstaking process. With this final, accurate diagnosis, we can create the perfect treatment plan. We can design the most efficient facilities, we can implement the best production strategies, and ultimately, we can maximize the amount of energy we can safely and economically recover. So it turns out that something as familiar as crude oil has this secret, complex personality that only really shows itself under extreme pressure. It really makes you wonder, doesn't it? What other materials that we use every single day have these complex inner lives that we're only just beginning to understand?